we are doing. The text is represented as a bag. Now, this bag is a data or a
Good morning, all. Am I audible? Very good morning. Am I audible? Okay. So once again, good morning. This is the video lecture on design and analysis of algorithms. We are currently discussing with a new topic, optimal binary search trees. So in the data structures, we have gone with a trees concept. So it is one of the non-primitive data structures where you come across the trees. So under these trees, we are having the concept of binary search trees. So binary search tree is a tree where root node will be, so root node will be greater than left child and root node will be lesser than right child. So that will be the binary search tree. Okay. So now in that you come for optimal binary search tree. Okay. So binary search tree is one of the most important data structure in computer science. So one of its principal application is to implement a dictionary, that is set of elements with the operation of searching, insertion and deletion. So one of its principal application is to implement a dictionary, that is set of elements with the operation of searching, insertion and deletion. The binary search tree for which the average number of comparisons in the search is smallest. So then we call it as optimal binary search tree. Okay. So binary search tree for which the average number of comparisons is small, then as possible, we call it as optimal binary search tree. So if the probability of searching for elements are known as optimal binary search tree can be constructed. If the probability of searching for elements are known as optimal, then the binary search tree can be constructed. Okay, so now you come for the optimal binary search tree examples. So consider 4 keys. So we are giving 4 keys here, A, B, C, D. Okay, so are to be searched with the probabilities 0.1, 0.2, 0.4 and 0.3. Okay, so 4 keys are given here. So are to be searched with the probabilities 0.1, 0.2, 0.3 and 0.4. 14 different binary search trees are possible. 2 of them are shown here. So we have given it as A, B, C, D, or you can also give it as in this particular form also. That is B, C, D, then A. Okay. So the average number of comparisons in successful search in first of these trees is given as average number of comparisons. So in the successful search in the first of these trees is, so it is given as 0.1 star 1, that is for A. So it is a first element, second element, third element, fourth element. So first element is 0.1 star 1, 0.2 star 2, 0.4 star 3, 0.3 star 4, that is equal to 2.9. So then you go with, so this particular tree, if this is the tree, you can tell this is at level 2, this is at level 1. So for level 2, A is at level 2. Okay, A and C are at level 2, B is at another level. So that's why you can give A is, so 0.1 star 2. Here you can see A was at level 1, level 2, level 3, level 4. But here it is A and C are at level 2, B is at level 1, and D is at level 3. Okay, so that's why A is given as, what is the A value? 0.1 star. What is its level? 2. That's why you are given it as 2 here. Next, B is at 0.2. So 0.2 star 1 plus 0.4 star 2 plus 0.3 star 3. Okay, so that will give 2.1. Neither of these two trees is in fact is optimal. So in that, which is optimal one, this is the most optimal tree what we are going to take. Okay. So optimal binary search tree. Okay. So when you go for the optimal binary search tree, so for our tiny example, we could find the optimal tree by generating all 14 binary search trees with this case. Okay. So how you find? So as a general algorithm, this exhaustive search approach is unrealistic. So total number of binary search trees. So total number of binary search trees with n keys is equal to nth catalog number. So that is, we are giving it as, so C of n is equal to 1 by n plus 1 into 2n. So this is a general algorithm which is used as exhaustive search approach. So that is given as catalog number C of n is equal to 1 by n plus 1 2n, which grows to infinity as factor of 4 power n divided by n power 1.5. Okay, so come for the problem definition. So under problem definition, given a sorted array A1 to AN. So how many elements are there here? It is a sorted array A1 to AN of such case and an array P1 to Pn of probabilities of searching, where Pi is the probability of searches to AI. Okay, so construct the binary search tree of all keys such that smallest average number of comparisons made in the successful search. So for that, so this is the problem statement. So what is in the problem statement? There is a sorted array A1 to AN of such case and an array P1 to Pn with probability. So I can tell you these are the 4 such keys with 4 probabilities. So this is, we have taken it as A1, A2, A3, AN, P1, P2, P3, Pn. So that is the A1 to AN and P1 to Pn, where Pi is the probability of searches to AI. Construct the binary search tree of all keys such that smallest array number of comparisons made in the successful search. So come for the solution. So solution using DP. Let A1 to AN be distinct keys ordered from smallest to largest, and P1 to Pn be the probabilities of searching for them. Let C of ij be the smallest average number of comparisons made in successful search in the binary search tree. So we are interested in just C of 1 to n. Okay, so C of 1 to n. So how to derive the solution? So to derive the recurrence, we will consider all possible ways to choose root AK among the keys AI to AJ. There are so many elements. So in that elements, you have to find the optimal way to choose the root AK. So how to find AK? AK is derived from AI to, so values are ranging from AI to AJ. So in between, if this is AK, so one element before is AK minus 1, one element after is AK plus 1. So keep in your mind binary search tree. So solution is, if you are having an element AK, so leftmost part, all the elements will be less than AK. So less than AK will be given as ai to ak minus 1, and the elements after ak will be giving it as, after ak is given as ak plus 1 to aj. So first element is ai, last element is aj. Element before ak is ak minus 1, element after ak is ak plus 1. So this is the binary search tree with root ak and 2 optimal binary search trees. So 2 optimal binary search trees. So that we can give in as, so how you give, C of ij is equal to I to k minus 1, k plus 1 to j. So it is given as, so min I to j in between k. Okay, here you can see it is starting at I, ending at j, in between you are having k. Element before ak is k minus 1, element after ak is ak plus 1. So min of C I k minus 1 plus C of k plus 1 comma j plus Ts. So this we assume this formula that C of I comma I minus 1 is equal to 0. So that we are taking like this one. Okay. So now you come for the example. So how to find the solution for that? So how you are finding the solution for that? So this is the elements you will be having. So these are the index values 1, 2, 3, 4. So in that you are having a key A, B, C, D. A with value 0.1, B 0.2, C 0.4, D 0.3. So you have to find, okay. So initially C of I comma j, for all the diagonal elements you should place 0. So 0. So here you can see 1, 2, 3, 4, 5. And here it is representing 0, 1, 2, 3, 4. So in that you are having 0, 0, 0, 0, 0. Okay. So now you come for the value part. At index 1, at index 1, that means 1, 1. Okay. So index 1 means, so row it should be 1. For column it should be 1. For index 2 means row it should be 2. Column also it should be 2. So 3 means row 3, column 3. 4 means row 4, column 4. So 1, 1 we take it as 0.1. Next 2, 2 we take it as 0.2. Next 3, 3 we taken it as 0.4. And 4, 4 we have taken it as 0.3. That is values 1, 2, 3, 4. Okay. So that is this is the representation. Now you are going to place the values. So now you find the values for remaining iterations. So here you are find for all these values. Now you have to fill the values for this particular thing. So in order to find C of 1, 2. Okay, 1, 1 is there, 1, 2, you have to find it. So C of 1, 2 is equal to, K is equal to 1. So when K is equal to 1, C of 1, K minus 1. So I value is 1, J value is 2. So I value is 1, that is K minus 1. K value is 1. 1 minus 1 is 0. So you should remember this formula. So this formula is used here. So I comma K minus 1 plus K plus 1 comma J. So I value is 1. 1 you put here. So K minus 1 is 1 minus 1 0 plus K plus 1 is 1 plus 1 2. J value is 2. So then again K equals 2. So when K equals 2, so it is 1 comma 2 minus 1, it's 1 plus 2 plus 1, it's 3. So J value is 2. So when you find this C of 1, 0, so C of 1, 0 is 0. C of 2, 2, 2, 2 is 0.2. C of 1, 1 is 0.1. C of 3, 2. So 3, 2 is nothing. You have to take it as 0. So plus 0.2 This is the formula. So when you go for minimum, so you will be taking it as 0.4. So what is C of 1 comma 2? C of 1 comma 2, we have taken it as 0.4. So that is the value, you can put it here. Okay, so similarly you have to find using this particular thing. So PS. So PS will be taking it as, so PS will be equal to 1 comma 2. At 1 it is 0.1, at 2 it is 0.2. So 0.1 plus 0.2 will give you to 0.3. So that is the total P you are having. Okay, this is 0.4. So C of 1 comma 2 is 0.4. Understood? So now that we have done, similarly you have to find out for all the values. So on finding all the values, this is the table you can find. So 1 on 1 comma 1, 0.1, 0.4, you should insert all the values like that. So after inserting all the values, now you come for the root table. Okay, so when you come to root table, it is 1, this one is a 2. So can you tell? So 1, 2, 3, 3. So you can take the values like that. 2, 3, 3, 2, 3, 4. So that is the root table what you are having. So when you have the root table, how to construct the optimal binary search tree? So when you are having the values like that, so optimal binary search tree will be given in this particular format. Okay, so come for the algorithm part. So algorithm, that is optimal BST. So what is the output? It finds the optimal binary search tree by dynamic programming. What is the input? It is probability for an array A of 1 to A of n with probability 1 to n for the sorted list of n keys. So what is the output? Average number of comparisons in successful searches in binary search tree. So for I equals 1 to n, say of I comma I minus 1 is equal to 0. First you put this particular thing. So I have shown in the arrow part. So C of I comma I minus 1 is equal to 0. So it is I comma I minus 1 is equal to 0. So C of I comma I is equal to P of I. So that is equal to this particular line. P of I. P of I is nothing but probability is what we have given for the problem. That is 0.1, 0.2, 0.4, 0.3. R of I comma I is equal to I. So R of I comma I is yellow border. So this is 1, 2, 3, 4. What you are giving the values. So that is 1, 2, 3, 4. That is root node. So finally, C of n plus 1 comma n is equal to 0. This is the last one you are having. Okay. So this is the optimal BST algorithm. So this is a formula we have taken. C of ij is equal to C of I comma k minus 1 plus C of k plus 1 comma j. So I is first, j is last. So in between you will be getting k minus 1, k plus 1 plus ps. For d ranging from, so for the diagonal elements. So d then 1 to n minus 1, I then 1 to n minus d. So j then I plus d. So this is the value what we have taken. So if C of I comma k minus 1 plus C of k plus 1 comma j is less than min-val, then take it as min-val is equal to C. So then take it as min-val is equal to C of I comma k minus 1 plus C of k plus 1 comma j. So R of ij is equal to k min. So this is the programming code what we have taken for finding the optimal binary search tree. So come for the analysis part. So coming for analysis, the algorithm requires, so how many loops you are getting? So 2 for loops, one for D, the other one for I. So this one will go with N, this one will also go with N. So N into N, it will be N square. So that's why you take, it takes N square time and N square storage. Therefore, as n increases, it will run out of storage even before it runs out of time. So if the number of elements keeps on increasing, if it will run out of storage even before it runs out of time. Okay, the storage needed can be reduced by almost half by implementing the two-dimensional arrays as one-dimensional array. So this will be the homework concept. So this will be the homework concept. Find the optimal binary search trees with the keys A, B, C, D, E with the search probabilities 0.1, 0.1, 0.2, 0.2, 0.4 respectively. So kindly go through this particular concept. So now you come for the next concept, that is knapsack problem. Okay, so knapsack problem that we have already discussed knapsack problem in greedy technique. The same thing you can solve it using dynamic programming also. So how to solve this particular knapsack problem? So come for the thing. So knapsack problem using DP, given n items of known weights W1 to Wn and values V1 to Vn and a capacity W. So find the most valuable subset of items that fit into knapsack. To so to design the DP algorithm, we need to derive a recurrence relation that expresses the solution in terms of smaller sub-instances. Let us consider an instance defined by first I items, I less than or equal to I, 1 less than or equal to I, now I less than or equal to n with weights W1 to Wi. So this is the knapsack capacity J. So J should be, what can be the capacity? It should be less than weights. Okay, so using DP. So how to solve the knapsack problem using DP? Let f of I comma j be the value of optimal solution to this instance. We can divide all the subset of first I items that fit the knapsack of capacity j into two categories. Those that does not include the ith item and those that do. So among the subsets that does not include ith item, the value of optimal subset is by definition f of I comma j is equal to f of I minus 1 comma j. F of knapsack problem using DP. So among the subsets that do include ith item j minus wi greater than or equal to 0, the optimal subset is made up of this item and optimal subset of first I minus 1 item that fits into an knapsack of capacity j minus wj. So the optimal solution among all feasible subsets. Optimal solution among all feasible subsets of first L items is maximum of these two values. So that is f of I comma j is equal to max of f of I minus 1 comma j comma vi plus f of I minus 1 j minus wi. So this is a formula what we are taking for finding the knapsack problem. Okay, so come for the algorithm part. So rather than going for the algorithm, I go with the example. So using example, you can easily understand. So weight item, you give it as 1, 2, 3, 4 with weight 2, 1, 3, 2 with a value $12, 10, 20, 50. So W is equal to 5. F of I comma j is equal to max of f of I minus 1 comma j. This is the formula. So initially W1 is equal to 2 with V1. So this is W part. W1 2, W2 1, W3 3, W4 2 with values V1 10, V1 12, V2 10, V3 20, V4 50. So come for the plotting of the thing. So write it as 0, 1, 2, 3, 4, here 0, 1, 2, 3, 4, 5. So find the composition of optimal subset by backtracking the computation. So what is the capacity they have given? Weight is equal to 5. So when weight is equal to 5, here you can see. So on 0, it will be everything is 0. Come for one part. So 1 on item number 1 and weight 2. It is you are written it as 12. Okay. So this is the only item. So at the level 2, weight 2, you are having 12. So assign it to 3, 4, 5 as well. So come for W2 is equal to 1. So at 2, at level 2 and at weight 1, you place 10. So I is equal to 2, J is equal to 1, you place 10. So I equals 2, J equals 1, you place 10. So this one will be 20. So now 3, 4, 5 has not inserted. So 10 plus 12 will go to 22, 22, 22. So come for weight number 3. So at I is equal to 3, J is equal to 3, you had 20. Okay, so I equals 3 and J equals 3. At I equals 3 and J equals 3. Okay, so I equals 3. Here you can see. So already this is the weight is 22. So 22, here it is 20. So that's why you give it as 22 remains same. So for that already 22 is there. In that, what is the maximum capacity you can go with? So remaining 8. So that's why you given it as 20 and 32 here. So finally, item row 4, column 2. At row 4, column 2, you can come for already 12 is there. In that, what is the weight you are having? 15. So make it 15. This goes 25. So this is the value how you are going to insert it for the knapsack problem. So come for the analysis part. The classic dynamic programming approach works bottom up. It fills the table with solutions to all smaller subproblems. Each of them is solved only once. Drawback. Some unnecessary subproblems are also solved. The time efficiency and space efficiency of this algorithm is theta of NW. So time and space efficiency is given as theta of NW. The time needed to find the composition is big O of N. So time and space efficiency is theta of NW. The time needed to find the composition of optimal is big O of N. Okay, so now you come for the discussion. The direct top-down approach to finding the solution to such a recurrence leads to the algorithm that solves common subproblem more than once. It solves the common subproblem more than once and very inefficient. Okay, since this drawback is not present in top-down, it is natural to try to combine the strength of the top-down and bottom-up. Okay, so now you come for the knapsack I, j. So now this implements the memory function method. So what is till now we have gone with only the knapsack of I, j. Now you come for the next topic, memory function knapsack I, j. So it implements the memory function method. So what's the input? So input a non-negative integer I indicating number of first items being considered and non-negative integer j indicating knapsack capacity. So output the value of optimal feasible subset of first items. So come for the algorithm. So go through this algorithm. J less than weight. So if j is less than weight, mf knapsack I minus 1 comma j. If j is greater than weight, max of mf knapsack I minus 1 comma j. So that we are taking it as f of I comma j is less than 0, then we take it as j less than weights. So we'll go with a value mf knapsack I minus 1 comma j, or if it is j is greater than weights, max of mf knapsack I minus 1 comma j. So values of I plus mf knapsack I minus 1 comma j minus weights of I. So come for the example, we have taken the same example. So they using memory function, you can directly go with this particular thing. So this is the values what how they are going to compute it. Okay, so this is up to knapsack problem, both a knapsack and a memory function knapsack function. Okay, so remaining thing. So in today's class, we have gone with optimal binary search trees as well as knapsack problem. So in the next upcoming class, you go with the remaining 3 topics of module 4. So I hope you all got understood this particular topic. So go through this video lectures in YouTube channel 1 DPMK. Kindly understand the concepts. So solve the problems. It is very, very important for the exam point of view. So solve the problems for that. Okay. So see you in the next upcoming lectures. So kindly like, share, subscribe for the channel and get the knowledge of the algorithms. So I hope you all understood the classes and topic. So I'll be ending the here class. So thank you all. Stay home, stay safe.